Negative 4, positive 2, so I go left 1, 2, 3, 4, up 2. And then I'm going to draw my radius. And then I'm going to drop my perpendicular. And that will give me my trigonometric triangle that I'm going to use to get all my values for SOHCAHTOA. And this angle here, remember, is going to be my theta. Now I know that it goes left, negative 4, and it goes up, positive 2. This side over here is opposite my theta. This side on the bottom is my adjacent to theta, my ADJ. And this really long side is my hypotenuse. Remember, SOHCAHTOA, that's going to equal opposite over hypotenuse. Ka is going to equal adjacent over the hypotenuse. And TOA is going to equal opposite over adjacent. But I need to find this hypotenuse first. And I do that by taking these values and throwing them down into the Pythagorean theorem here. I add it. Now, if you brace that up, it's going to be the same as just 4 squared. And when I type that in, that's going to be 4 plus 16. That's root 20. And that breaks down to 4 times 5, or 2 root 5 is my radius or my hypotenuse. 2 root 5. The calculator will do it for you. So now this is going to be opposite, or 2 over 2 root 5. Let's simplify that right now. That's going to be 1 over root 5 because those 2's will cancel out. Adjacent over hypotenuse, that's going to be negative 4 over 2 root 5. Let's simplify that right now because negative 4 divided by 2 is negative 2. So that's going to give me negative 2 over root 5. Tangent is just going to be 1 over negative 2. Opposite over adjacent, or this number over this number, and because it's already simplified, it makes a convenient move for me. Now, cosecant is just a reciprocal function. That's going to give me root 5 over 1, or just root 5 if you want. This is going to give me root 5 over negative 2. And this is going to give me negative 2 over 1, or just negative 2 if you want. Now I'm going to come back and fix these. If you don't know how to do it by hand, you can use the calculator and just type it in. But this will simplify to root 5 over 5. This will simplify to negative 2 root 5 over 5. Remember, you have to simplify them and not and rationalize the denominator. Now I'm going to find theta, and I can use this one if I want. So that's going to give me arc sine, remember, to the negative of 1 over root 5, or root 5 divided by 5. But you have to be careful with when you end the root 5. And when we type that into the calculator, that's going to give me shift sign, and be sure you're in degree mode, square root of 5. That's going to give me 26.56 degrees, or right around 27 degrees. A equals half of that. B equals that root 3, 4 root 3. Over here, this is a square, so this side's going to equal 7, this side's going to equal 7. This F is going to equal 7, and E is going to equal 7 root 2 for 45. Now I have a 30, 60, 90. I know it doesn't ask for H, but if you were asked for H, it would equal 14, and I would equal 7 root 3. And then I would go ahead and fill this in carefully. A equals 4, B equals 4 root 3. C equals 7, D equals 7, E equals 7 root 2. Don't forget the 45 is a root 2. F is 7, and I is 7 root 3. Review of sine and cosine. So I need my amplitude, and my amplitude is going to be the absolute value of negative 2, so it's just going to be 2. What that means is I go up 2 and down 2 from the origin and draw a sort of boundary, kind of a horizontal asymptote at y equals 2 and y equals negative 2. Then I need the period. In order to find the period, I place a 2 pi on top of pi over 2. So I'm going to do a little arithmetic up here. 2 pi divided by pi over 2 is the same as 2 pi times 2 over pi. And notice the pi's will cancel out, and that will give me 4. So the period equals 4. I'm going to go out 1, 2, 3, 4, and place a 4 there. Take half of 4, that will give me 2. Half of 2, that will give me 1. And I know that's going to be 3. Now the sine curve starts at 0, 0. And then it's supposed to go up. But because it's negative, it's going to go downward. And I'm going to get this pattern bouncing about. And we want to continue the pattern all the way at both ends. Bouncing along. And it will end up there. In the reverse order, it's going to bounce up that way. And now we're going to connect those dots with a curve, please. And it goes pretty smooth. Then we go right to secant. Now, in order to graph secant, I have to do its reciprocal function, cosine. There's no trick to it. Usually you think that begins with an S, that you do the sine function, but it's counterintuitive. So I'm going to graph cosine 2x first. Notice my amplitude is 1. So I'm going to go up 1, down 1. And draw my horizontal asymptote. The period, I place a 2 pi over that 2, and that will just give me pi. So I'm going to go out 4 units and place a pi there. 1, 2, 3, 4, and that's going to be pi. Now half a pi is pi over 2. Half a pi over 2 is pi over 4. 1 pi over 4, 2 pi over 4, that's going to give me 3 pi over 4. Some people just multiply that by 3 to get 3 pi over 4. Cosine doesn't start at 0, 0. Cosine starts at 0, 1. And then it's going to bounce. Here's the deal, though. I'm not supposed to be graphing cosine. I'm actually supposed to be graphing the secant curve. This is just a helper curve to help me eventually graph the secant curve. So I'm going to continue my cosine dots where they belong. And then I'm just going to do a light curve of the cosine, because I'm really not supposed to be graphing cosine. I'm supposed to be graphing secant. So this is a helper curve. It's not the curve that I'm supposed to be graphing. We call it an auxiliary line or an auxiliary curve, sort of like a catalyst in science class. I am not done. Wherever this cosine function goes through 0, secant is equal to 1 over cosine. So wherever it's 1 over 0, that's where cosine is 0, I'm going to have an undefined spot or a vertical line. In this case, it's considered a vertical asymptote. Wherever it goes through 0, I'm going to have the vertical asymptote. And I'm going to have many of them throughout this curve. And this is going to give you the actual shape of the secant curve. So I'm drawing all these vertical asymptotes where it goes through 0. Now that I have my boundaries, I have my horizontal boundary, and my vertical boundaries, where the cosine curve is tangent to the boundary, to the amplitude, you're going to draw an upside down or unlucky horseshoe, parabolic. Now we're going to draw a lucky horseshoe. Again, quite parabolic. And we're going to continue this process. Where it touches, there, that point of tangency, we're going to get that U, some people call it. It's not really a parabola because it is bounded. It doesn't have a domain of negative infinity to positive infinity. It is a bounded curve. It is parabolic in nature, though. And that completes our graph of secant 2x. Graph of 2 cosecant pi x. Now, the question you want to ask yourself is what basic graph parent function is related to cosecant? And that graph would be sine. So I'm going to make an attempt to graph 2 sine pi x. The amplitude is 2. So I'm going to go up 2 and down 2 from the origin and put my boundary, my horizontal asymptote, or my amplitude. And then I put 2 pi on top of pi and simplify that, and that's just going to give me 2. So my period equals 2. I'm going to go out 4, 1, 2, 3, 4, and put 2 there because I need 5 important points. So half of 2 is 1, half of 1 is 1/2, and then I multiply that by 3, and that gives me 3 halves, or 1.5. Now, again, I'm trying to graph the sine curve, which is related to cosecant. So sine starts at 0, 0, and then it's going to start to bounce. And these are going to be my important points as I go along here. Again, I'm not supposed to be graphing sine. I'm supposed to be graphing cosecant. So these are just helper points. These are auxiliary points that are going to help me to finalize and graph cosecant. Now, some of my students have said that they don't like graphing the auxiliary curve, and I'm perfectly fine with that. You can just utilize the points if you wish. But for educational purposes, I'm going to continue to graph the sine curve if anybody needs any review on graphing the sine curve. So let's see, there we have it. Now, same idea. Wherever the sine curve goes through 0, cosecant is equal to 1 over sine. So that's going to give me a 1 over 0 scenario. And whenever I have 1 over 0, that's going to give me a vertical asymptote. So once again, I'm going to have many vertical asymptotes. Notice what I do on the y-axis, so I know that the y-axis is also a vertical asymptote. And these vertical asymptotes are going to be the boundaries for those parabolic curves or those horseshoes or U's, whatever slang you want to use to get the idea across of what this curve looks like in the end. Notice, I have like a half of a lucky horseshoe over here. And now I have a full unlucky horseshoe. A lucky horseshoe, an unlucky horseshoe. It's unlucky because it's upside down and the luck can fall out. A lucky horseshoe. Notice, if I would put some luck in that horseshoe, it would stay in. A little bit of superstition. Lucky horseshoe, lucky horseshoe, half of an unlucky horseshoe. Tangent. If you notice on the unit circle, where the tangent is undefined, it's at 90 degrees, or pi over 2. So that's where my first vertical asymptote is going to be, where tangent is undefined. So I'm going to go right 2 units, and I'm going to put a pi over 2 there, and that's going to be my first vertical asymptote. And that's where this is undefined. Now, using that rationale, if I were to go backwards 2, that would be negative pi over 2, and that would be my other vertical asymptote. Tangent is a little difficult because it straddles the xy axis, and half of it is in the positive, and half of it's in the negative. Notice, this is 4 units long, so what's half of pi over 2? That's going to give me pi over 4. And then over here, this is going to give me negative pi over 4. Now again, if I look at my table of values, and I want to know what tangent of 0 is, notice, tangent of 0 radians is 0. So that's going to give me a coordinate at 0, 0. Then, tangent of pi over 4. Tangent of pi over 4 is going to give me, let's see what pi over 4 is. There's pi over 4, and I go up to tangent, it's going to give me 1. Tangent of pi over 4 is going to give me 1. So I'm going to plot a point there. Now, if I were to graph this from where that is, notice what it looks like. It's going to come through those 2 points, and then hit that vertical asymptote and go north. Now, likewise, tangent of negative pi over 4 is going to be negative 1 if you use a little interpretation, and then the graph is going to go down to negative infinity. Now, this is going to continue every 4 spaces because it's periodic. And notice, this point is going to mirror, this point is actually going to slide, and I'm going to have the same curve going through those points identically, but shifted to the right. Now I'm going to be attempting to graph cotangent, and the deal is I like the cotangent because on all of my tables, it's right down at the bottom, so there's cotangent. I want to figure out where cotangent is undefined, and right off the start, it's undefined at 0 radians. Then I scroll to the right, and it's undefined over here at pi radians. So I'm going to go 4 units. I'm going to include 0, a vertical asymptote, and pi, a vertical asymptote. So let's see. If I go from 0, that's a vertical asymptote. And notice how I put these dashes on the y-axis so that I know that's a vertical asymptote, and I go right 1, 2, 3, 4, and remember that was pi. That's going to give me my other vertical asymptote. And if I go over another 4, it's going to be cyclical or periodic. That's going to be my other vertical asymptote. I want to find out what these points are, so what's half of pi? That's going to be pi over 2. Half of pi over 2, that's going to give me pi over 4. If I multiply that by 3, that will land me at 3 pi over 4. Now I want to find out what these coordinates are. I wonder what cotangent of pi over 4 is. Cotangent of pi over 4 is 1. So I'm going to put a dot at 1. Cotangent of pi over 4 is 1. I wonder what cotangent of pi over 2 is. Cotangent of pi over 2 is 0. Cotangent of 3 pi over 4, cotangent of 3 pi over 4 is negative 1. And it lines up pretty nice. Now I can see that that's going to repeat, so I'm going to repeat those coordinates on the right over yonder. And the cotangent curve is going to come like this, go through those 3 points, and then go downward. Same process repeats on this other section. I don't require you to put the other points, but some people do. Horizontal and vertical asymptote techniques. The first thing we need to do is set the bottom not equal to 0, but I just set it equal to 0, so that means I would add 1. That would give me a vertical asymptote at x equals 1. So I'm going to go to x equals 1 and strike my vertical asymptote. Now I need the horizontal asymptote. To find the horizontal asymptote, you need to look at the degree of the top. And the degree of the top expression is 1. Then the degree of the bottom, that's 1. Since the degrees are the same, you look at the leading coefficient. So the leading coefficient is 2 on top, and the leading coefficient is 1 on the bottom. So the horizontal asymptote is going to be y equals 2 divided by 1, or just y equals 2. And there it goes. Whoop, it's going to be at y equals 2, so that's a horizontal line, vucks away to y equals 2, and I just want the asymptote. You don't actually have to graph the curve. For number 9, again, notice, the degree of the top is 2, the degree of the bottom is 2. But I'm going to find my vertical asymptote first. In order to do that, I have to factor. And I'm going to factor the top. It's going to be x times x equals x squared. 2 times 2 equals 4. And then the signs have to alternate, positive and negative. And when I use the ZPP, the zero product property, that's going to give me x equals negative 2 as a vertical asymptote. There that is. And x equals positive 2 as a vertical asymptote. There's that vertical asymptote. Horizontal asymptote, I noticed the degree of the top is 2, the degree of the bottom is 2, so the degree of the top is equal to the degree of the bottom, and that's going to be the leading coefficient divided by the leading coefficient. Y equals 1 is my horizontal asymptote. And again, I'm not asking you to graph the curve, just the asymptotes. Over here, we should be able to graph the curve. This here is a phase shift of the parent function, 1 over x. And the intersection of asymptotes is going to be located at the opposite and same of that. So that's going to give me 1, comma 2. So I go right 1, up 2, and that's going to be my intersection of asymptotes. And if we recall, this is the one that the video game designers used to help invent and fly asteroids. The intersection of asymptotes for this one is again going to be opposite same, so that's going to be negative 1, comma negative 1. So I go left 1, down 1, and I put my intersection of asymptotes for this phase shift of the parent function 1 over x. I'm going to go diagonal 1, and the curve is going to come in and have asymptotal behavior.